So now that we have all of these parameterizations in our pocket, let's go ahead and put them to good use. We want to talk about scalar surface integrals. So the idea here is that this is going to generalize our surface area calculations from section 16.5. For section 16.5, we took our surface S, we parameterized it like R of UV, and we found the surface area as the double integral over, some domain R here in the UV plane of the absolute value RU cross RV. And the idea here is that, whenever we're calculating out area, we're like integrating 1 over some reason. So there's a fake 1 that's implicitly in there. The idea behind scalar surface integrals is that now, instead of this being 1, we want to change this to be some function. Wrote capital G here. And the idea, okay, so at some point, I should be a little bit formal here and say, how are we doing these calculations? Anytime we have an integral, well, maybe we should be thinking about, some kind of Riemann sum. Okay, so here is our surface. And so the idea here is that, and again, this should feel familiar from section 16.5. We're going to break it up into lots of little, sub chunks here. And in section 16.5, to find the area, we're going to be integrating 1 on each of these little chunks, and as we make the chunks of area smaller and smaller and smaller, they'll flatten out. This is the basic idea here. But, and so there's a limit of, this kind of thing as the number of chunks goes off to infinity, as the chunks become smaller and smaller and smaller. Now the idea is that on each chunk, this is like X, Y, and Z, we're going to compute G of X, Y, Z on that little chunk. We're going to compute G of X, Y, Z on that little chunk. We're going to compute G of X, Y, Z on that little chunk. We're going to do a test point on each little chunk there. We're going to multiply the value of G of X, Y, Z by the area of that little chunk. And we're going to do the same idea as we make the chunk smaller and smaller and smaller. And so this is a definition, a somewhat formal definition. I probably left out some details. You can see the textbook for complete definition. But this is what we look like for a scalar value function, capital G of X, Y, Z, some surface S. The surface integral, maybe I want to say the scalar surface integral of G over S, is the double integral over S of G of X, Y, Z, d sigma. It's equal to the limits n goes to infinity of, and then this right here is just saying, well, this is the area of a chunk times the value of G at some point chosen on the chunk. And then we do a limit as we get in, the number of chunks goes off to infinity, the size of the chunks goes down to 0. This is our formal definition. Now, obviously, we really don't want to have to do this kind of definition here all the time. And so what we want to do instead is use parameterizations. So take a look here. Here's our chart for how we are going to evaluate scalar surface integrals. First step is that we need a parameterization, R of UV. Then we're going to find R of U, R of V, the cross product of those, the absolute value of the cross product. And then we just evaluate our scalar double integral, scalar surface integral, by substituting in our parameterization into the function we're integrating times the magnitude of the cross product here of the partial derivatives. So that's why I, made this chart here, because anytime that your surface falls into one of these buckets, we can, quickly say, oh, okay, so we have r of xy is graph of, our surface is a graph of function. Here's our r of xy. We can instantly just go ahead and write down this magnitude of cross product there. That makes our life really easy. I'll also point out, to wrap up things here, this should feel very similar to our scalar line integrals calculation. How do we compute a scalar line integral? We had a parameterization of our curve. We took our parameterization, we substituted that into the function we're integrating, and then we multiplied it by the magnitude of the derivative of the parameterization. That before there was a magnitude of r prime of t. Now there's a magnitude of r sub u cross r sub v. In some ways, this is playing the role of the derivative of r of uv. This should feel very, very familiar. Okay, so that's introduction to scalar surface integrals. We'll do a couple examples in upcoming videos.